Welcome to the deep dive. This is where we take complex research, pull it apart, and give you the key insights, nice and clear.
Yeah, perfect for anyone who wants to, get up to speed on tricky topics without drowning in detail.
Exactly. And today we're tackling a really interesting paper. It's called Don't Be Lazy. Complete Lazy enables compute-efficient deep transformers.
That's the one. We've got some excerpts here. It's paper 2505.01618V1 if you're looking it up. And our mission really is to figure out how to train these huge, large language models, LLMs, more efficiently.
More efficiently meaning less cost, better results for the compute power you put in.
Both, ideally. It's about understanding that whole relationship between how big the model is, all those fiddly settings, the hyperparameters or HPs, and the sheer computational cost involved. How do we get smarter about building these things?
Okay, let's get into it then. So the basic premise, everyone kind of knows this. Bigger LLMs tend to perform better, right? They understand more nuance, handle trickier tasks.
Generally, yes. But, and this is the huge but, making them bigger means the compute cost, it just explodes. It doesn't scale nicely.
Right, it's not just a little bit more expensive, it's massively more expensive, like needing a whole new power station just to run a slightly bigger machine.
You hit the nail on the head.
Yeah.
And it's not just the overall size, the number of parameters. It's also figuring out the best shape, how wide versus how deep should it be.
Okay, explain width and depth quickly again.
Sure. Width is sort of how many calculations happen in parallel within a layer. Depth is how many layers you stack up, how many sequential steps it takes.
Got it. And those, plus the dataset size, the batch size, how many examples it learns from at once, they're all these hyperparameters.
Exactly, HPs. And choosing the optimal mix of all those, especially when you have a fixed amount of computing power you can actually afford, well, that's the challenge.
It sounds incredible.
That's a good analogy. Just randomly trying different HP combinations on these massive models. You can, and people do, burn through staggering amounts of compute on setups that just, well, don't perform well. It's incredibly inefficient.
Okay, so we need a smarter way than just guessing.
Precisely. And this leads us to the idea of parameterizations. Think of them as like intelligent rule sets, guidelines for how to adjust your model settings and your training settings as you scale the model up.
Ah, so it's a strategy for scaling, not just making things bigger haphazardly.
Yes, exactly. And a really important concept here is something called AP, or the maximal update parameterization.
AP.
AP. It's a technique designed to help keep the best hyperparameters, like the learning rate, relatively stable, especially when you're scaling the width of the model.
So if I make my model wider, Key helps me predict what the other settings should be.
Sort of, yeah. It aims to make those optimal HPs less sensitive to changes in width. This enables what they call a tune small and train large approach.
Tune small, train large. That sounds practical. You figure out the best recipe on a small, cheap model.
And then you can be more confident applying those settings when you build the full-scale, expensive version. It saves a massive amount of that trial and error guesswork on the big model.
Makes sense. So how does this new paper build on AP?
Well, it takes that core idea and refines it, specifically looking at how to scale both width and depth together effectively. And a key difference in their approach compared to standard P lies in how they handle the outputs from the transformer's residual blocks, especially concerning the network's depth, which they usually call L.
Residual blocks. Right. Those are the core building blocks in transformers. So they adjust how information flows through them based on how deep the network is.
Exactly. They looked at this core equation. Don't worry too much about the symbols, but it's like the output of the next layer, A plus 1, equals the input, H, plus some scaled version of what the layer actually computes.
LF, L minus alpha. What's the key thing there for us?
The key thing is that L to the power of negative alpha bit. Alpha is the crucial parameter here. Think of it like a dial, controlling how much you downscale the layer's contribution based on the total depth. A bigger alpha means you scale it down more aggressively as the network gets deeper.
So it's a way to manage the signal as it goes through more and more layers.
Precisely. And this paper really zeroes in on two specific values for alpha, 0.5 and 1.
Okay, 0.5 and 1. What happens when they set alpha to 1?
When alpha is set to 1, that defines this specific parameterization they introduced called CompleteP.
CompleteP, okay.
And their big claim is that CompleteP ensures something they term complete feature learning when you scale up both width and depth.
Complete feature learning sounds important. What does it mean practically? Like the model learns properly at every level.
Kind of, yeah. Imagine if a layer becomes lazy, it just sort of passes information through without really transforming it much, maybe just doing something close to a simple linear tweak. Complete feature learning means every layer, even in very deep networks, keeps actively learning complex, nonlinear stuff based on its inputs and its own parameters. It avoids that laziness.
So the depth is actually being used effectively, not just making the model bigger.
Exactly. And what they found empirically, like in their actual experiments, was pretty compelling. Setting alpha to 1 using CompleteP was consistently more compute efficient than using alpha 0.5.
More efficient? How so?
They suggest it's because CompleteP allows for better transfer of those hyperparameters from small models to deep ones, and it also seems to speed up the actual pre-training process itself. They show this visually in their figure 1.
Interesting. So it saves compute and makes tuning easier for deep models. Is it simple to use?
Relatively, yes. But they do stress that to get the full benefit, you need to do more than just set alpha to 1. You also need to apply their principal scaling rules to other things.
Like what other things?
Things like layer norm parameters. Layer norm helps stabilize training the learning rates, specifically for bias terms, the weight decay setting in the Atom W optimizer.
Atom W, the optimizer a lot of these models use. Weight decay stops it from just memorizing the data, right?
Yeah, right. Prevents overfitting. And even a tiny parameter in Atom W called epsilon, they provide specific guidelines for scaling all of these, detailed in Table 1.
So it's a more complete package, hence the name.
Exactly. It's simple to implement, but the full CompleteP involves these coordinated scalings. And the payoff seems to be superior performance and efficiency, particularly as models get deeper and deeper.
Okay, so let's break down the main contributions. What are the big takeaways from this research?
Well, first is that hyperparameter transfer across depth. They directly compared how well key HPs, like the base learning rate and the initial weight settings, transferred when you change the depth. They looked at the standard approach, SP, AP, and their alpha equals 0.5 and alpha 1 CompleteP methods.
And CompleteP was the winner.
Hands down, their finding 1 states pretty clearly that SP, P, and the alpha 0.5 approach don't keep the same optimal HPs when you vary the depth. You'd have to retune.
But with CompleteP.
Finding 2 says that only CompleteP, alpha 1, gives you reliable HP transfer across depth, even when you're trying to train it in the most compute-optimal way possible. Figures 2 and 3 in the paper really illustrate this. The performance stays strong for alpha 1 as depth increases, while it drops off for the others if you don't retune.
Wow, okay. That alone seems huge. Being able to tune on a smaller model and scale the depth reliably, that saves, potentially, a massive amount of compute.
It really does. It reduces that expensive search for the right settings on the giant models. Second big contribution, optimal shape and compute efficiency.
Shape meaning the width-to-depth ratio again.
Yes, the NLA ratio. They built scaling laws for models from 75 million up to 1.9 billion parameters, all trained efficiently using about 20 tokens of data per parameter. And they use this setup to re-examine what the best NL ratio actually is when you use proper scaling like CompleteP.
And what did they find? Did CompleteP save compute there too?
Significantly. For their 1.9 billion parameter models, using alpha 1 saved almost 12% of the FLOPs, the total computations compared to MP, if they used the optimal shape for each. But even more dramatically, for very deep models, like 179 layers deep, the saving jumped to over 34%.
34%, just by using this complete VP scaling. That's enormous for these huge training runs.
It really is. Which ties into their third point, refining the criteria for good HP transfer, leading to that concept of complete feature learning.
Right, the non-lazy learning.
Exactly. They argue that a key goal, a desideratum, for any good parameterization should be ensuring that every layer stays active and learns nonlinear features relative to all the parameters before it. And they argue only alpha 1 achieves this, hence CompleteP.
So it's not just about stable training, it's about making sure the model is actually learning effectively throughout its depth.
That's the idea. And fourth, they provide those extra HP guidelines we mentioned for layer norm, bias learning rates, weight decay, Atom W epsilon scaling them with both depth and width. Table 1 and Appendix E have the details. They note these are especially crucial for stable training if you would use alpha equals 0.5.
It sounds very thorough, a complete system for scaling.
That seems to be the goal.
So this changes how we should think about that width-to-depth ratio, NL. I thought there was a rule of thumb, like NL should be around 100.
Yeah, that came from earlier work, often based on parameterizations like P that maybe didn't fully capture the depth scaling dynamics as well. This paper is one of the first, they claim, to really study compute optimal NL while properly controlling for both infinite depth and width limits using alpha equal 1.
And what did they find? Is 100 still the magic number?
Not necessarily. Finding 3 is that the optimal NL ratio actually tends to get larger as the overall model scale increases, regardless of the parameterization. So bigger models might prefer to be relatively wider.
Okay, so the optimal shape changes with size. What else?
Finding 4 reinforces the efficiency point. CompleteP, alpha 1, gives you increasing FLOP savings over T, specifically for deeper models. That 34% saving we mentioned is an example.
Right. More savings the deeper you go.
And finding 5 is really interesting. It says that as models get bigger, CompleteP uniquely allows models that are deep but relatively narrow, so a small NL ratio, to stay close to the compute optimal performance curve.
Wait, so with CompleteP, you could potentially build very deep but not necessarily super wide models and they'd still be efficient.
That seems to be the implication, yes. Figure 4F in their paper illustrates this. Other parameterizations see efficiency drop off much faster if you make models deep and narrow, but CompleteP handles it better.
Why is that flexibility useful? Deep narrow versus shallow wide.
It could have big implications for hardware. Shallow wide models are often easier to parallelize, which is good for latency-sensitive tasks where you want a fast answer. But deep narrow models might require less memory per layer, making them potentially better suited for deployment on hardware with memory constraints, like maybe edge devices or phones down the line. CompleteP needs use more options.
Ah, okay. Matching the model shape to the hardware constraints. That makes a lot of sense. So better efficiency, better HP transfer, more flexibility in shape. Does it actually perform better on tasks?
Good question. And yes, it seems so. They tested 1.5 billion parameter models, trained with CompleteP on a bunch of standard benchmark tasks. HelloSwag, ARC-Easy, Lambda, Race, PQA, BoolQ. These test things like common sense reasoning, reading comprehension, question answering.
A standard battery of LLM tests.
Exactly. And Table 2 shows that the upstream pre-training gains they got with CompleteP generally translated into better performance on these downstream tasks, compared to models trained with other parameterizations using similar compute.
So it's not just faster training, it's actually leading to potentially smarter models for the same cost. It's a genuine win-win.
That's what the results suggest, yes.
Now, you mentioned they had some theoretical backing for why CompleteP works, these desiderata.
Right. They proposed 3 desirable properties, or desiderata, for constructing good parameterizations that handle scaling well.
Okay, what are they?
Desideratum 1 is stable initialization. Basically, the model shouldn't explode or vanish at the very start of training. All the activations and the output should be well behaved. They show this implies alpha needs to be at least 0.5.
Makes sense. Can't learn if the model blows up immediately. What's number 2?
Desideratum 2 is maximal residual stream update. This is a bit more technical, but the gist is that the learnable weights in each residual block should contribute meaningfully, like order 1 over L, to changes in the features flowing through the network, while non-residual parts contribute a constant amount. This leads to a specific scaling rule for the learning rate involving alpha.
So ensuring updates are happening at the right scale throughout the network.
Kind of, yeah. Ensuring the updates are effective and proportional to the depth. And the third one, which they highlight as novel, is Desideratum 3, complete feature learning.
Back to the non-lazy learning idea.
Exactly. This desideratum states that no part of the network, hidden layers, or the output should become asymptotically linear or lazy with respect to any subset of the model parameters as the model grows. Lazy learning essentially means the network isn't using its nonlinear capabilities effectively, hindering deep learning.
And CompleteP Alpha 1 is the only one that satisfies all 3.
According to their analysis, yes. They use a simple example of a 2-layer block, equation 6, figure 5, to show how setting alpha 1 prevents a kind of lazy behavior that can happen with alpha 0.5 as depth L goes to infinity. So, finding 6 sums it up. Only CompleteP ensures stability, maximal updates, and complete feature learning as both width N and depth become very large.
It seems like a very well-reasoned approach then, tying the theory to the empirical results.
It does seem quite coherent, yes.
So wrapping this up, what are the main practical takeaways here? If I'm someone trying to build or train LLMs, what should I remember from this?
I think the key points are complete AOP. Using that alpha 1 scaling seems to offer much more reliable hyperparameter transfer across both model width and depth. This can lead to significant compute savings, potentially over 30% for very deep models compared to BOP.
Big savings. Don't forget the extra HP guidelines, too.
Right. To get the full benefits, you also need to use their scaling rules for things like layer norm parameters, bias learning rates, weight decay, and atom W epsilon. It's a package deal.
And it's relatively easy to implement. They released code.
They say it's simple, and yes, they mentioned a public code release, which is great for adoption and verification by the community. Their plan is to use this to train even bigger models.
Any broader impacts they mention?
They touch upon the potential positive side effects. Improved efficiency could mean lower energy consumption for training, reducing the environmental footprint. It could also lower the barrier to entry for training large models, making cutting-edge AI research perhaps a bit more equitable.
Those are important points. Any limitations we should keep in mind?
Sure. They acknowledge their experiments focused on decoder-only pre-layer norm transformers using the AtomW optimizer on text data. How well it translates to other architectures, optimizers, or data types needs more research. And of course, they were limited by their own compute budget in how large they could test.
Standard caveats for this kind of research, but overall,
CompleteP looks like a very promising and practical parameterization. It tackles the depth scaling challenge head-on, seems to avoid lazy learning, and offers real compute efficiency gains. It feels like a significant step forward for training truly deep transformer models effectively.
definitely sounds like it. It provides concrete benefits for researchers and companies trying to push the boundaries of LLMs, especially under real-world budget constraints. It really opens the door to thinking differently about model shapes too.
Absolutely. More flexibility, potentially better performance for less cost.
Okay, this has been a fantastic deep dive, really illuminating. So here's something to think about for you, the listener. Given these trade-offs between width and depth and how CompleteP seems to make deep, narrow models more viable, what kinds of new model architectures or maybe even specialized hardware could become more attractive or feasible now? Definitely some food for thought there.
Yeah, it could shift how we think about designing efficient AI systems.
We definitely encourage you to check out the original paper if you want to go deeper. Thanks for joining us for this deep dive.